Okay, let's begin. Welcome everyone to the Astronomical Society of Edinburgh. A few technical issues here, so things are not quite as smooth as they usually are, but we'll get through it. It's working okay. We've got something here. The main event of the evening is we've got Dr. Ben Giblin telling us about the light, shedding light on the dark side of the universe with gravitational lensing, and Neil Martin will be telling us about the sky in Mark. Yep, that's what we've got coming up. So I've just got a few news items, just what's happening in the society, what meetings are coming over the next month, and then our two talks for the evening, and we've got tea and coffee at the back as well. So quite a lot of people joining us at the moment. We had quite a handful last month, and we got another handful this month. So I don't know if any are here, but Donald, Brian, Tommy, Ivan, Stuart, and Neil, if any are here. Love to meet you, but welcome everyone. I say we have 219, but that will drop very shortly for the people who haven't renewed from last year, and Alan's going to do his Grim Reaper job very shortly. So, as I mentioned before, there was a partial solar eclipse on the 29th of March, Saturday morning, and we are hoping to live stream that from the Cook Telescope on Calden Hill, which Will has been organising with the collective up there, and members will be up there with, you lot will be up there with solar telescopes as well. I've got a bundle of eclipse glasses as well that we can hand out, and it's the same as we did in 2022. Those are the timing, so it's reasonably civilised. It starts about 10 o'clock in the morning and ends around about noon as well. And this is what happened last time we were up there, using the Cook to do a live stream of that, and those are our members outside with solar telescopes, and people were very interested. We had the BBC News up last time. I suspect they might be up there again this time as well, but you never know with the media. So if you're able to come up there, then please do, and if you've got solar telescopes, we would really like to bring them up. More details about that later on. Okay, the next talk, so on the 12th of March, that's Wednesday, next Wednesday, we have for AZ members our Imaging and Observing Group meeting, and that will be on Zoom. On the 21st of March, our next meeting is an online-only meeting, and that's about neutrinos and missing antimatter from Dr. Susan Cartwright. And then, as I mentioned, the partial solar eclipse. And the next in-person meeting here will be on the 4th of April, and that's a members' night, so we'll be having short talks from members. I don't know if we're full yet with speakers. Are we not? Not quite. So we still have we have spaces if you would like to give a short talk, 5, 10, 15 minutes. Good to hear from you. And visitors are welcome as well. You don't need to be a member to come to that. That will only be on, that will be in here, and it'll be on Zoom. It won't be on YouTube, that one. A bit of housekeeping. So council elections are coming up. I've been mentioning this quite a lot. At our AGM in June, we'll be needing nominations for places on the council, and all of the roles and places on the council are going to be available. So please consider getting involved. If you don't do it, no one else might do it. So there are 200 plus people, so let's hope we can get a good number of people signed up to be on the council. The posts are now for 2-year terms, and we've just had our first 100 years, so let's set the direction for the next 100 years. And it is good fun to do. It's very important for the society, and it's not too onerous. We have a council meeting every couple of months. So all the 5 office bearers are up for election: President, 2 VPs, Secretary and Treasurer, and a space with 9 council members as well. Up to 2 of those can be remote members, as we have at the moment. But Sean will be sending out more information on that very shortly. This is my regular plea for volunteers, as I do all the time. We do have a few things to do around the society. Tea and coffee, an example of that. Peter Mulholland, who does it normally, isn't great at the moment. So we do need people helping out with that. Tech desk, we have spaces for help on that as well. We're doing a lot of outreach at the moment, which Andrew's doing an amazing job with that. We're always looking for people to help with that. Scouts and guides and the like often ask us to help out as well. So we have 200 plus members, lots of people in the society. So if you'd like to get involved, well, we really need you to get involved in the things that we do. That's it from me. So I'm going to hand over to Ben now. If I can just find you the slides. Yep, on you come. Yep.
I'm amplified, lovely.
Yes,
okay, good. That's for me. Thank you. Down arrow, and I have a laser pointer. Super. Okay, great. Yeah, thank you very much for having me. I've never been to speak here before, even though I've lived in Edinburgh like 10 years, so it's a real pleasure to do an astronomy talk just on my doorstep. So yeah, I'm Ben Giblin. I'm a Stephen Hawking Research Fellow at the Institute for Astronomy, which is at the Royal Observatory on Blackford Hill. And here tonight, I'm going to be talking about how we can shed light on the dark side of the universe with gravitational lensing. So by the dark side of the universe, I'm talking about the parts of the universe that are essentially not directly observable. We tend to observe these things and detect this side of the universe indirectly with one of a number of cosmological probes. And the cosmological probe that I work with is gravitational lensing. Okay, so this is all about cosmology. So if you're not familiar with the word cosmology, I'm sure many people are in an astro society, but cosmology is the science of how the universe formed and how it's evolved over billions of years. So this inevitably becomes a study of what is the structure of the universe on the largest scales, like billions of light years. And what is that structure made of? So yeah, this is basically astronomy on the largest scales there are. And cosmology at the moment is at a crossroads, okay? Yeah, so there's a number of things that are keeping cosmologists awake at night. One of the first and most important ones is that dark matter and dark energy remain a mystery. So these are two extremely important ingredients of our universe that we're going to talk about tonight, and we don't really understand them at all on a fundamental, like theoretical level. Another thing that's keeping cosmologists awake at night is the fact that multiple cosmology surveys conducted by independent teams on different sides of the globe that are all observing the universe at different points in its cosmic evolution, these teams are returning discrepant results. So results that do not agree. And that could be because someone's made a mistake, but it could be because we don't understand the universe quite as well as we think we do. So there's a crack in our standard model of cosmology. So that's kind of keeping us awake at night. And so it's not clear where we're going to go from here. And I think something that I think is very important to think about is like, how did we get here in the first place? How did we arrive at this time where it feels like sometimes it can feel like there's major flaws in cosmology. So we're going to explore some of this tonight. Okay, so if you only take one thing away from this talk, it's that cosmology is a piece of cake. And by that, I mean, if you were going to create a universe, this feels like an appropriate room to ask this question. So imagine you're God or a sort of omnipotent cosmic creator, and you were going to create a universe. I would suggest you approach this in much the same way that you would approaching the baking of a cake. Okay, so I'm showing a universe on the right-hand side here. This was not created by God. This was created by a numerical simulation team. So this was created on a computer. And what you're looking at is what we call the cosmic web. So this is an enormous spider web measuring billions of light years across. And these red sort of structures that you can see here, those are basically big structures of matter, which is primarily dark matter in our actual universe. And at the sort of intersections of these points, you would expect to find big clusters of galaxies and lots of galaxies sort of clinging to the arms of this enormous large-scale structure. So this is the sort of thing we study as cosmologists. And if you wanted to create something like this, you would need two things, the same two things that you would need if you were going to bake a cake. The first thing is you need a recipe, okay? And when we're thinking about the large-scale structure of the universe, we think we do know the right recipe. And so that recipe is the laws of physics. And with the structure of the universe on the largest scales, the forces of nature that are the most important and the most dominant are gravity. So of course, there's other forces at work in the universe, but on the largest scales, gravity is the one that has the biggest impact on that enormous cosmic web that you just saw. So the recipe that we have for gravity comes from Albert Einstein. This is the general theory of relativity. This is just a screenshot of one of his papers on this subject from 1950. So we think we know the recipe for how this large-scale structure formed. However, this recipe, it's kind of, I'll say the second thing you would need, which you would also need for baking a cake, is ingredients, okay? And the ingredients determine the output, right? So that's kind of obvious. If you look at these ingredients on the left-hand side here, it's clear you're not going to make like a shepherd's pie out of these things. They determine the output to some extent. They still have to go through a recipe, but yeah, there's only a limited range of things that could come out of these ingredients. So what are the ingredients of our universe? When people started performing cosmology experiments for the first time, they knew some of the ingredients of our universe. You know, there is the matter of which we are all made. There's the periodic table. There's the particles that we consider fundamental in our universe. But it wasn't clear that those were the only ingredients of our universe. So what else could there be? And normally when you get a recipe in a recipe book, you would hope that that recipe tells you the quantities of each ingredient that you need for that cake, you know, like 500 grams of flour, 2 eggs, whatever. But the recipe that we have ourselves for the universe, that of general relativity, it's kind of a lot like the recipes that you get as a contestant on the Great British Bake Off, okay? So if you've seen this show, you know there's a technical challenge where they're tasked with making something and they're not really told exactly how much of each thing to put into that. They're just like, add flour, you know, okay, so how much? General relativity is a lot like that. It says, there are some ingredients here, but for our actual universe, we don't know the quantities exactly of each one. So we're kind of approaching this from reverse. It's like we've been presented with a cake, and we think we know the recipe, but we don't know how much of each thing went into that cake. So when we start thinking about the ingredients of the universe and we write them down, this is the kind of list that you come out with. So these are what we call cosmological parameters. These are the free parameters in our recipe for the universe. Okay, so we've got the Hubble parameter, named for the famous American astronomer. This is essentially a measure of the rate of expansion of the universe. You can think of it that way. Secondly, we've got the matter energy density for the universe. This is basically how much matter is in the universe. This second parameter, the baryon density, this is the amount of the universe, or rather the amount of matter, which is the particles that we're made of. So like the stuff you can think of as the ordinary particles, the stuff in the periodic table. And if this is the only kind of matter that exists in the universe, you'd expect this omega m and this omega b parameter to be the same, okay? So spoiler alert, we find out they're not the same. And there's a lot of matter in the universe that we don't understand on a fundamental level. Another parameter that comes up is the cosmological constant, omega lambda. So lambda was a term that Einstein introduced to his equations out of prejudice. So basically, he recognized that if gravity is the only force that is dominant on the largest scales, then and gravity pulls things together, there's really nothing to stop the universe from collapsing. And he didn't like that idea, okay? So he thought that the universe should be steady state. It should have always existed and it shouldn't ever collapse. So he introduced something that behaves like the opposite of gravity to counteract that term. He later went on to describe this as his biggest mistake. It turns out that this was the right thing to do, but for the wrong reasons. So he introduced it to make the universe static and not expanding, not collapsing, just static. Turns out that this thing does exist, but the universe is not static. It is expanding, and not only that, it's accelerating in its expansion, is what we found out when we went out and measured these things. There's a bunch of other parameters here. I'm not going to go through all of them, but essentially our job as cosmologists, like in practice, is to measure the values of these things for the real universe. So we're trying to figure out how much flour, how many eggs, how much sugar went into this cake that we are inside of, to stretch the analogy a bit too far. Okay, so yeah, and basically, I know there's a lot of parameters here, but you can make some assumptions, and our recipe for the large-scale structure of the universe, it often boils down to just 5 free numbers. So 5 free parameters describe the entire universe, which is quite exciting. We just now need to go out and measure them. And that is what has been done over the past few decades. An enormous progress has been made, and it's produced this pie chart that I'm sure a lot of people have seen before. I like to call this the humble pie chart because it's very embarrassing for cosmologists, because basically it says that more than 70% of the universe is this dark energy stuff that's accelerating the universe's expansion, this lambda term. Then about a quarter of the universe we find out is dark matter. So this outnumbers regular matter a factor of 4 to 1. So if you add up dark energy and dark matter, it ends up being about 96% of the energy density or stuff in the universe. And that means that the stuff we actually understand, the stuff in the periodic table and these things called neutrinos, those only add up to about 4-5% of the universe. So this is embarrassing for cosmologists, I should say, because it is it's our whole job to measure what the universe is made of, and we find out we don't understand 96% of our job description. So it's not great. Okay, but how did we get here? How did we decide or find out that we don't understand 96% of the universe? So one of the strongest pieces of evidence for what I've just told you comes from the study of the cosmic microwave background. This is some of the strongest evidence for what has been called the standard model of cosmology, which is often shortened to lambda CDM. So lambda is that dark energy stuff accelerating the expansion of the universe, the cosmological constant, it's also called. And CDM stands for cold dark matter. So we name the theory after the things we don't understand and the things that make up the majority of stuff in the universe. So this is the cosmic microwave background. So this is that microwave radiation that exists in every direction you look on the sky. This is a radiation left over from the Big Bang. And what you can see as you look from left to right here is how the resolution with which the temperature fluctuations in this radiation has improved over time as the instruments that observed the CMB, cosmic microwave background, have improved. So the best picture we have of the CMB here comes from the Planck telescope. And so these temperature fluctuations, they might look large just from this picture, but these are actually extremely small, and it took a lot of effort to measure these. So these are temperature fluctuations at the order of about 1/5000th of a degree. And why is this important to measure? Well, the cosmic microwave background is so interesting and such a rich source of cosmological information, because what you're looking at here is a battle map between two opposing forces in the universe. In the red regions, that's where gravity is winning. And gravity seeks to push things together and create regions of higher density. Whereas the blue regions here, that's where the other side is winning. And that other side is radiation pressure that seeks to prevent things from being pushed together, arbitrarily close. So it's the same kind of forces that stop you putting your hand straight through a table. That's the pressure between particles. So this is so important and so useful to measure for cosmology because these are the seeds of the density fluctuations from which that cosmic web will later grow. So I didn't say that this is kind of a snapshot of the universe as it was in the early days when it was only 300-ish thousand years old. But we know that these tiny temperature fluctuations grew, and they grew into high density regions. And if we were to overlay the cosmic web that we observe in the real universe today on top of this map, we would see things like mega galaxy clusters coincide with these higher temperature regions because they're the high density regions. So this is the seed of our universe. So if you can measure this and find a way to summarize it on a statistical level, this can tell you the values of those cosmological parameters that you're interested in. So how much matter is in the universe? How much of that matter is baryonic, so the ordinary stuff that we're made of? How much does dark energy play a role in this? So the job of the cosmologists who worked on this survey was to summarize this information in some statistical way that they could compare to a model that comes from our recipe. So the Einstein's theory of gravity, essentially, we can compare our measurement of this to what the recipe tells us it would be for given values of those parameters. And then we can fit those free parameters in the model and figure out what the ingredients of the recipe should be. And that's basically what is shown here. So this y-axis here is basically the strength of those temperature fluctuations. And on this x-axis here, we have as a function of angular scale on the sky, where over at this end you have smaller angles, and on this end you have larger angles. So how strong are the temperature fluctuations on different scales? And these blue things are the measurement from the real universe, and then this red line, which goes through them perfectly, that is from our recipe, from the standard model of cosmology, lambda CDM, which is built on Einstein's theory of gravity. And this, for a lot of cosmologists, is just like a surefire sign that this model must be correct, right? Like it fits these points so well. It's like kind of like looking into the face of God almost, like we've cracked it. Like we do have the recipe correct. So on the, I should say here, this is just the ratio of these points to that red line. So you can see that there's scatter, but they're all just perfectly on it. And so this cosmic microwave background, it told cosmologists a number of exciting things. It told us that omega lambda, which is the amount of dark energy, that is dominant over the amount of matter. So there's more dark energy in the world than there is matter, and that's that's basically the reason our universe is accelerating in its expansion, because dark energy is pushing things apart and it's dominant over the matter, which wants to pull things back together. It also told us that dark matter dominates over ordinary matter. So of the matter that exists, this omega C term, that's the amount of cold dark matter, and it's 4 times bigger than the number which corresponds to ordinary matter. So that's how we know 80% of the matter in the universe is dark matter. And this also basically told us perhaps the most exciting thing, which is like maybe the least quoted, is that this is consistent with our Big Bang model, that the universe had a beginning 13.8 billion years ago. So yeah, it was an amazing cosmological experiment. And you could be forgiven for, when this result came out, you could be forgiven for thinking, well, cosmology is over. Like, we've solved it. This is the answer. The recipe's correct. We've figured out the numbers. It's done. Like, we can go home, right? And, well, we still don't know what dark matter and dark energy is, but that might be, you know, a problem for the particle physicists. They can figure out what dark matter is. We're done. I wish that was, I don't wish that was the case, actually, because it keeps me in the job. So it isn't the case. So, as I said, there's other things keeping cosmologists up at night, and one of them is tensions. And this is this idea that different surveys disagree on the values of these numbers. So on the y-axis here, we've got the measured value of the Hubble parameter. This is that thing that kind of measures the rate of expansion of the universe. And this is how estimates of that number have evolved over a few 20 years, basically, in different publications. And the blue lines are measurements that come from that cosmic microwave background measurement that you just saw. This can be compared with some other measures, which are observations of things that are the more recent universe, shall we say. So these are things like supernova explosions. These explosions are very useful probes for figuring out how fast the universe is expanding. And basically, you can see that as time has gone on, the measurements of this parameter have diverged. And this shouldn't happen, right? Like, we're observing the same universe. We should get the same numbers. And the fact that we're not getting the same numbers, and the difference between these numbers is now so massive, these error bars do not overlap. This is very strong evidence for either someone in multiple teams actually has made a mistake that is creating this discrepancy, or it's a sign that the recipe is wrong, that lambda CDM isn't the right description of the large-scale structure. This isn't the only tension that we're seeing. So this is another cosmological tension. So on the x-axis here, you have this matter energy density, amount of matter in the universe. This thing here, sigma 8, measures how clumpy that matter is, so how strongly that matter kind of sticks together. And these kind of banana-shaped contours here, these come from something called weak gravitational lensing. So this is what I do, and we're going to talk about that in a second. This other measurement is from the cosmic microwave background, and the fact that this thing and this thing do not overlap, that's tension. That's saying we disagree on the values of these numbers. And yeah, this is another sort of compelling reason to think that something's wrong. And something's wrong in either multiple teams or the recipe is wrong. So yeah, it's quite exciting. Okay, so let's talk about gravitational lensing. This would have been a video, but we're now on PDF for technical issues. So you'll just have to imagine this. So you can imagine a distant light source that's giving out light rays. And we're over here on Earth. In between this galaxy and Earth, we would, if the video played, a large galaxy cluster would grow. And the gravity of that very compact object would begin to bend these light rays so that they curve towards the Earth. And what we would see on Earth is something like this smiley happy face. It's not always a happy face. But essentially what you're seeing here is these arcs of light. And this is because the light from that distant galaxy has been bent by something along that line of sight. And that thing along the line of sight acts like a lens. So it's kind of like you've held up a magnifying glass. And the impact is that you can often see multiple images of that background object. So these arcs are like that background object stretched out. around the compact object, which is in the middle, which was a galaxy cluster. So this is the images of gravitational lensing that you mainly see. And this is actually strong gravitational lensing, okay? This is not what I do. This is very easy. It's not easy for anyone who does strong lensing. But I say it's easy because it's obvious. Like, you can immediately spot strong gravitational lensing. I actually do weak gravitational lensing. And the reason that I think weak gravitational lensing is so cool is that strong lensing only happens in small, isolated, compact places on the sky. So when you've got a very big galaxy cluster, for example, that's bending this light very strongly, do you get this impact? Weak gravitational lensing happens everywhere else. It happens everywhere on the sky. So this is another computer simulation that kind of tries to illustrate what is going on here. So these little blue dots, they represent distant galaxies. And this sort of confetti-looking stuff, that's that cosmic web again. So with weak gravitational lensing, what we've got is the light from these galaxies on its way to us observing it, and you can imagine we're the observer on this side of the box. The light is constantly being lensed by this large-scale structure, by a very small amount. And so this is us. This is the view as you look through this box. And what you see is all of these galaxies that you observe, their shapes are very slightly distorted by this lensing effect. So it's much, much smaller than in the strong lensing case. And it can also change their orientation so that they start to align. Sometimes I like to explain this as, this is kind of like looking at coins at the bottom of a well. So you can imagine these coins are all the galaxies that you're observing. And even though the thing that is between you and those coins is transparent, which is the water, you can tell that that water is there because it's distorting your image of the coin that you're looking at. So that's basically what dark matter is doing. So dark matter, it's actually a bad name. It implies it's darkly colored. In fact, it is transparent like water. But we can tell that it is there because it's bending the light from those distant galaxies and distorting their shapes. So as I said, this is weak lensing. The impact on an individual galaxy is very, very small. It's actually unobservable, basically, for an individual galaxy. And that's why you have to observe millions of them, okay? And if you observe millions of them, then that signal, that gravitational lensing signal, starts to stand out when you start to add it up, basically. You need an awful lot of these galaxies for this small distortion to stand out above the noise. Okay, so I want to take a second to tell you about a previous generation of weak lensing surveys. So this survey was called the Kilo Degree Survey, or KIDS. It's what I spent my whole PhD working on. It was a bit confusing sometimes when I said, I've been doing a lot of work with kids recently. People thought I worked in a kindergarten or something. So this was a ground-based survey, and it used the survey telescope on the VLT, which stands for Very Large Telescope. It was not an imaginative name, which is based in the Paranal Desert in Chile. No, I never got to go. It is a great regret of my life. But what kids did was observe about 1,000 square degrees on the sky. So that's about 1/40th of the sky. To put that in context, it's about the area of the sky that would be covered if you held both your forearms up to the sky. That amount of sky is what we covered. And in that amount of sky, we observed 27 million galaxies. And we measured all the shapes and orientations of those galaxies, and we used the amount of lensing that those galaxies had experienced to map out the large-scale structure of the universe. And that's what is shown here. So this really is the real universe now. These bright spots are high density regions in the universe. So wherever there was a greater amount of lensing, we were able to say there's more matter there. And where there was less lensing, we could say there was less matter there. And that's how you can create this picture of the cosmic web. And when we made this, this was briefly the largest map of the dark matter structure in the universe that had ever been made. Another survey made another map 6 months later that was larger. So that was very sad. Yeah, and I say dark matter structure. This is actually ordinary and dark matter that's being mapped out here, but because dark matter is the majority of the matter, you can think of this as primarily a map of dark matter. So kids, it took images that looked a bit like this. So if you're unimpressed by this, that's fine. Like this, in a way, this was state of the art when it was done. This took 13 years, this survey. So this is one exposure from the survey. It's in black and white, but the actual original images were in color. You've got all these sort of strange artifacts, which are sort of bright stars that were blocking our view of the background that we wanted to mask out. This big green streak is when a satellite flew across the image. So thanks, Elon Musk, we had to get rid of that. And yeah, so this particular image, I don't know how many galaxies it contains, but let's zoom in on one of them. Let's zoom in on this. So this is a zoom in of that region. You can see that this galaxy is pretty pixelated, okay? And we're being generous here. We're picking one of the biggest things in this field of view. We could have picked that thing. That's like 3 pixels. And what we're trying to do here is use images of galaxies that are like this and like that to detect this tiny amount of lensing signal, this tiny change in the galaxy's shape that came from this gravitational lensing. This was a really challenging measurement to do. But it was done because we had so many galaxies that even if individual galaxies kind of looked a bit rubbish, we still had so many of them that we could get a convincing measurement of this signal. So this was what the previous generation of weak lensing surveys looked like. I now work on a new survey, and this new survey is Euclid. So Euclid is a space telescope. This was launched in 2023 from Cape Canaveral in Florida. I was very, very lucky to go there. I'd only been working on the survey about 6 weeks when I went out there, and it was quite an experience to be standing at Kennedy Space Center with this about to launch. And there were people shoulder to shoulder with me who'd been working on this thing for about 15, 20 years, and they were absolutely bricking it. And I'd been working on it 6 weeks, and I was like, well, yeah, I hope it doesn't blow up, but you've definitely got more skin in the game than I do. So this launched in 2023. It is going to cover 13,000 square degrees on the sky. So that's about 1/3 of the sky. It's 13 times more than that kids survey I just showed you. In 1 year of observations, it has taken more data than any other weak lensing survey in history did over 10 plus years. And it is going to observe more than 1 billion galaxies. And this is it in the labs. I think this was in France where this was taken. I never got to go see it, but you get a sense for its scale. It's about the size of a minivan or something. And let me give you an idea now of the type of imaging that Euclid does. So this would have been a video. This would have been quite an effective illustration, but it's fine because I have a backup slide to illustrate the imaging. But yeah, let's skip to that. This is the type of images of galaxies that Euclid takes. If you compare that to this pixelized thing here, this is what we're working with Euclid. It's like comparing video game graphics from the 1980s to like a PlayStation 5. So we have so much more information with which we can measure galaxy shapes now. And not only are we going to have, imaging that is this beautiful, we're going to be observing more than 1 billion galaxies with this kind of resolution compared to like a few tens of millions before. The statistical information that we get from Euclid is absolutely insane. And the reason that, well, you know, one of the reasons that we get this beautiful clarity of imaging is because Euclid is in space. So the light from those galaxies no longer has to make it through Earth's atmosphere to hit our telescope. And Earth's atmosphere is not ideal for astronomy for a number of reasons, but you know, it's good to breathe, but it doesn't help with imaging. So it's amazing to have Euclid in space. So what are the things Euclid is going to give us? So it's going to give us a 3D map of the universe tracing the last 10 billion years. So we're going to have an unprecedentedly precise image of this large-scale structure. It's going to tell us, is lambda, this cosmological constant, the correct description of dark energy? Or could dark energy be evolving over time? So lambda is quite a rigid model. It says that dark energy it basically stays the same energy density level over time, whereas a more complex model could, in principle, be possible. So dark energy might have been a different level at one point in the past compared to today. So this is something really exciting that Euclid's going to tell us. Basically, is the recipe correct? Will the cosmological tensions be solved? Will Euclid, as the most powerful survey ever conducted of this kind, have the final word and tell us what the values of these parameters are? The rest of you were making mistakes. Go back to the maths and figure it out. And it's going to tell us as well, is Einstein's model of gravity the best description of our universe? Or is an alternative model of gravity preferred? So yeah, it's extremely exciting. It's probably the most exciting time to be in this field ever. So Euclid will tell us, is this a recipe for success or for disaster? And the final thing I'll end on is that cosmology this was a GIF as well. He was doing anyway, it doesn't matter. Cosmology is a human endeavor, so all of this is only possible with like amazing people who work on Euclid. And so I have a little project called Humans of Euclid, which we're on Instagram and on Blue Sky. We were on Twitter, but then we stopped liking Twitter as much for some reason. But yeah, if you want to learn more about the people who work on Euclid, then we post these on Blue Sky and on Instagram, and we have like little interviews with the people who work on Euclid. Okay, I think that's me. Thank you very much.
Thank you. That was excellent. Really good. Yeah, we're not on Twitter anymore either. We're on Blue Sky too. Any questions, Ben? I'll go to the close one first.
Thanks for a great talk. Is Euclid your own personal space telescope, or have you got to share it with other people?
I wish it was my personal telescope, but it is in a sense a personal telescope to the Euclid consortium. So Euclid is one of the reasons it's so good is that it was purpose built to perform weak gravitational lensing observations. So that's its primary science goal. It also measures another probe, which is how galaxies cluster together, but it's really designed for that, and the data is sort of prioritized to the people who are working on that science and are tasked with making this whole thing work, basically. It does have a couple of other science-like objectives that it is effective at as well. So it can detect like high redshift galaxies. It tries to avoid the ecliptic plane that we are in, so it's not ideal for solar system astronomy, but it does sort of just about touch close enough to the ecliptic that some solar system scientists are interested in the observations as well. So, but it's primarily for weak lensing and galaxy clustering, and the data is like pretty much targeted towards this consortium of people who are tasked with working on it.
In the kids survey, you showed a close-up image of what you describe as a galaxy. How do you know it's a galaxy?
When I picked that one out, I was actually not sure if it was a galaxy or not. That is actually a really good point. So when we have all of these things, we want to separate the things we're seeing into two camps. So we're seeing stars and we're seeing galaxies. The galaxies are the things that are being lensed because they're far enough away for their light to have passed through this large-scale structure. So we do need to separate them and figure out which are which, and it isn't always obvious. One of the ways this is done is that stars and galaxies tend to have different colors. So we observe these things in a number of color bands, and then we can plot their colors and we can see, the galaxies cluster up here, the stars are down here. Then there are some inconvenient things that are sort of in the middle, but we try to draw a line between them and say, those are our stars. They are useful actually for something, but the galaxies, those are the things we want to measure the shapes of and detect the lensing of. So it's primarily based on their colors that we separate them.
Jim, do you want to?
Okay, I've just got one thing to say myself since I have a microphone.
Are you there?
The analogy of the bake-off was very interesting, because on that very stage, once the gentleman that you had in your slides once prepared a very, very tasty cake that had to be in the fridge for 24 hours, so the audience had all gone home and only the caretaker was left to eat it. Anyway, who else?
It's amazing.
Hi, on your second last slide, where you had a number of points,
Yeah.
it wasn't obvious in terms of what the how the Euclid data would answer these questions. Could you elaborate a wee bit on those, please?
Yeah, sure. So, so for example, is lambda the correct description of dark energy, or does it evolve over time? So this is a similar kind of exercise to what I showed with the cosmic microwave background. What we're doing here, though, is instead of measuring temperature fluctuations in something, we're measuring these galaxy shapes, and particularly the correlations in those galaxy shapes. And that tells us something about how much matter is in the universe and how strongly that matter clusters together. Because essentially, if there's more matter and it's more clumpy, then we have more lensing, and galaxies that are separated on the sky that shouldn't in any way be correlated in their shapes end up correlated because their light has passed through the same stuff. And so by essentially measuring these correlations, we can compare that to a model which comes from this recipe, this standard model of cosmology. And the strength of that measurement from the recipe depends on these three parameters. One of the things it depends on is like this dark energy parameter. And so we can sort of toggle the strength of that parameter and see what best fits the data. And so the projections are that Euclid will answer this question of like, is this dark energy model that we have correct? It will answer that to within about 1%, that basically this dark energy thing is constant over time. That's kind of a postulate of this standard model. So it's all because the strength of these correlations that we see in galaxy shapes depend on this thing. So we can use those measured in the real universe to figure out what this is. So also to answer like how Euclid might answer this one, this is an exercise in basically taking other recipes that people have come up with, sort of modified gravity theories, these are often called, and seeing if any of those can provide a better description of what we observe in the data. And if any of those can do that without requiring dark energy and dark matter to exist, that would be really quite compelling, because it would be interesting if we could explain the large-scale structure of the universe without invoking the existence of these things that we don't really understand that well. No one has yet been able to come up with a theory of gravity that can simultaneously explain all the observations of the universe, like cosmic microwave background, gravitational lensing, without having some dark matter and dark energy ingredients in there. So it doesn't look like they'll bite the dust anytime soon. I hope that answered your question.
Okay, I think this is a follow-on question. I'm curious if you're looking to expand the number of parameters by, say, allowing lambda to evolve over time, or if you look at updated models of gravity, where do you look at the evidence for one versus the other? And I use that word, you probably realize why I use the word evidence, but how do you compare multiple models to determine if adding extra parameters is justified by the data?
Yeah, that's a really good question, because of course, if you added an infinite number of parameters to your model, you can fit anything. And so, so when we do this, when we fit these free cosmological parameters in the data, we are doing Bayesian statistics. For those who don't know what that is, it's good. I just Google it, it's really good. But yeah, so one of the things that goes into that is this kind of Occam's razor effect, where you basically say the simplest explanation of this data is right. So you downweight models that have more parameters in them, that have more freedom, to counteract that effect that you could explain anything if you just have more parameters. But if that effect of downweighting that model because it has more parameters is counteracted by the fact it just really, really well describes the data, then there's this balancing act. Like maybe it was worth adding those extra few parameters. So yeah, this is all to do with this Bayesian evidence quantity that you calculate. Sorry. Yes, yeah, Bayes factors, yes. Yeah.
Well, thanks very much, Ben. That was absolutely fascinating. I just was wondering, the billions of galaxies, or the billion of galaxies that Euclid's looking at, are you revisiting those galaxies? Because if you're to take your analogy of the coins at the bottom of the pool, you're looking for tiny changes in measuring tiny changes in the shape. Yeah. So are you revisiting those galaxies many times over to do that, to see that distortion?
Yeah, I did think about, I think this is the point where that analogy with the coins breaks a little bit, because of course with the coins that water is changing in real time, and that's changing the distortion of those coins in real time. That isn't the case with the galaxies we're observing, because that large scale structure is fixed, at least on human timescales. It is evolving over, mega years and billions of years. But so we don't revisit them because we wouldn't expect anything to have changed in the large scale structure between us and that galaxy on our timescales. But if we were to perform this measurement again in a few million years, then yeah, there would be changes that would be really interesting, because they tell you about how the universe has evolved between the last time you observed it and this time, which I think would be very cool.
I think it was the third last slide. You showed a Euclid image of a galaxy. I wonder, how would you actually categorize its distortion?
Good question. So very, very crudely is what I would say to this. So when we measure the shape of galaxies, we basically just fit an ellipse to it, and we say it's like, it's sort of this long in this direction, that long in the transverse direction, and that's it, which is very crude because galaxies can have all kinds of crazy shapes. But yeah, but we have like over 1 billion of these, so you can't really measure each one really sort of robustly. But yeah, so we're basically just quantifying the shape of this thing as how elliptical it is and its orientation. And yeah, what we're then doing essentially is, so we didn't know what this galaxy looked like before it was lensed. So we don't really know exactly how much its shape has changed due to lensing. And this is what I was saying about correlations before. The way we pick out the lensing impact on this galaxy's shape is by looking at the correlations in galaxies whose shapes should not be correlated if lensing had not happened. So we've got 1 billion of these. We can measure the correlations in these billion galaxies. And without lensing, there should be no correlation. It should be 0 signal. But because it isn't 0, that is what's telling us this lensing is happening. So yeah, we can't see it for an individual galaxy. It can only be picked out sort of statistically with millions and billions of them.
Thanks. Near the beginning of your presentation, when you were introducing strong lensing, you showed a picture image and there were sort of 2 galaxies and then stuff round about. If you go to that slide.
Yes,
that one. Is that actually the bright ones? Is that actually 2 completely separate galaxies, or is it one that's been imaged in different ways?
I'm not certain. I think those could be part of the foreground galaxy cluster rather than something in the background. But yeah, I'm not actually certain of that though. Yeah. So yeah, they're probably part of I think the thing in the middle is probably the galaxy cluster itself that's causing the lensing, and these might be 2 particularly bright things that belong to that cluster, but I'd have to go back to this is a very famous Hubble Space Telescope image. So
it's a nice smiley face.
Yeah,
anyway.
exactly. That's why it made a lot of headlines, but I'd have to look again to be sure.
Ben doesn't do strong gravitational lensing.
It's not my bag.
Have you got anything on Zoom or YouTube? No.
Yep, we've got a question here on YouTube from BTT. How will the SKA Observatory be contributing to the field of gravitational lensing surveys and research when it starts early science operations in the late 2020s?
The SAA?
The SKA, I believe.
Oh, the
that's
SKA,
the
sorry,
large
yeah.
radio telescope.
So, yes, the SKA, the Square Kilometre Array, is a radio survey, which is it's based in South Africa, I think. So I have friends who work on this. So weak gravitational lensing is very hard to detect with in the radio. And that's partly because, so I'm not a radio astronomer, but from speaking to radio astronomers, my understanding of it, it's often very hard to localize things on the sky very well. The flip side of radio astronomy is you often have very, very good estimates of distances to things, which is very useful. But in weak lensing, we need to have very good localization of objects on the sky in order to measure their shapes. And so radio weak lensing is very difficult. So it's not that no one's doing it. People are trying to do weak lensing with radio astronomy, but it is at the point optical. So this is all optical astronomy. It's where optical weak lensing was about 25 years ago. So it's playing catch up, and it could in the future be a very powerful complementary kind of probe to optical weak lensing, but I wouldn't expect Well, yeah, I wouldn't expect SKA to be that helpful with measuring galaxy shapes. It could, in principle, be useful with measuring the distances to them. And that is that's a very important thing to have when you do this type of analysis as well. Not only do you want to know the shape of a galaxy, you want to know how far away it was, because did its light pass through a whole load of large-scale structure or just a little bit? That's really important to disentangle those effects. SKA might help with that. And my cousin, who's a radio astronomer, has said you need to write a fellowship proposal about how we can use radio observations to complement what you're doing. So I think that's a really good idea, and I should go write that down.
Thank you. Going back to the last but one question, this slide that's showing at the moment, does it matter to you how far away the galaxies are over this vast distances, or is it simply the number you can get that give you the data? You know, if you think of the comparison with the optical lens, is there any such thing as a sort of focal length of one of these lensings?
So I think I definitely understood the first part of this question. I might need to come back to the second part, which was, we do care about how far away these galaxies are. And that's, that's essentially to do with this effect of, we want to be able to tell the difference between, if a galaxy is very close and it's showing a lot of lensing, that means there's an awful lot of structure between us and that galaxy. If it's been really strongly lensed, then and it's quite close, then it meant there had to be a lot in that short slice of the universe between us and the galaxy. Alternatively, it could be much further away, showing the same amount of lensing, and what we're really seeing and living in is a universe that is a lot smoother than that other scenario. So that we want to be able to disentangle those two effects if we're going to correctly estimate these cosmological parameters. And that's why we care about distances. I think there was a second part to it.
I think you've answered the second part. I was thinking of whether you would know whether it was a dense lens or whether it was just an effect of distance. And you're saying that you are going to try and unscramble that. So thank you.
Cool, thanks.
Well, lots of great questions. If there's nothing else, then I think you can thank Ben again. Thank you.
Thank you.
And if you hang around for coffee afterwards, Mike will badger you about more details of the statistics you're on about. Now we're going to have The Sky in March from Neil Martin. So we'll just get set up here. Just move my bag.
Bear with me.
Messed around with Neil's display settings while we were using his PC, so it'll take a while to get going.
And I think I've shot myself in the foot by making it more complicated than it needs to be. So here we go. Right, so I'm Neil Martin. Mic's working, yeah? Yeah. I'm Neil Martin, and this is the sky in March, or at least the rest of March. So here's a roundup of my tour for this evening. We'll start with when it's light and when it's dark, which is always quite handy. We'll see when what I call the big night light is on, and what else it's up to. I'll share some details of when to observe our planetary buddies, including the ones who are not around this month. Oh, man. It must be the cable. I didn't touch it, honest. It was, oh, there we go, it's working again. Right. Shout if that goes off. Yeah. Yeah, the planetary bodies are not around this month. I'll point out how the sky changes over the month and highlight just a couple. Shall I plug it back in again? It's the cable. It was. Yeah. I know that Ben had to do his presentation without video. I don't know if I can do mine without anything. It is just keeping. It is just. I wonder if I can try a different route around the back.
Got a man with a cable.
I mean, the one thing I'll say about the sky in March, it's going to be dark, so at least some of the time. Here we go. It's come back on. So I wonder if that's.
Keep at it for now.
Keep at it for now. Okay. Yeah, I'll highlight a couple of interesting constellations to take a look at, and some deep sky targets. And I'll remind you, should that be necessary, of a couple of important calendar or clock events. And the part I referred to at the start about making this more complicated, I thought it would be quite interesting to switch between slides and use of Stellarium, which is one of my favourite bits of software. And in my notes here, I've got, I wonder if that's a little bit ambitious. I think I've answered my own question. So yeah, this could go one of two ways. So let's see. Let's see what happens. Also, kicking off with when it's going to be light and when it's going to be dark. And these are details for Edinburgh tomorrow. Nice sunrise at 06:45 and sunset at 18:02. And by the end of the month, it'll still be 6:45 for sunrise. I think that's some sort of magic. But by the end of the month, for reasons we'll get onto later, sunset is at 19:49, just before 8 p.m. So the bad news is that we're down about 2 hours in terms of ideal conditions for observing. The alternative view is that we spend less time worrying about what the weather's doing. And I've listened with great joy to people like Alan doing these sessions in previous months and talking about the different twilight levels. And I've often found it difficult to sort of visualize what that actually looks like. Those of you who know me know that I'm a kind of, well, it's 10 o'clock, it's dark outside, maybe I'll go and try and do some observing. So I wondered what it might look like. And so let's see how Stellarium can help us visualize that. Now, so this is a view of Stellarium that I messed about with to make sure that things were working properly. And on my other display here, hidden to you guys at the moment, I've got the Stellarium remote control. So I'm going to do some stuff with sleight of hand. So let's see what happens. One of the things I need to do is turn on the date time window. So keep an eye on that in the bottom corner of the screen. Those of you at the back have got no chance. So I've set this to twilight, just before twilight tomorrow, or as I call that, dark. It's night time. And then I'm winding on time using Stellarium scripts to see what the different twilight levels look like at the points that they start. And I found that really helpful. So now I can see that in astronomical twilight, it should still be possible to do some observing. But the time you get to this point, daytime, then we're into the realms of solar observing and solar imaging and so on. So that's the kind of thing that we can do with the combination of Stellarium scripting and remote control interfaces. And we'll come back to that later. So back to the slides. Mark's already mentioned the partial solar eclipse on Saturday, March the 29th. These timing details are taken directly from the Sky Diary page on our website, so feel free to refer back to those. You've got about 3 weeks to get ready and get set. Methods for observing this in person: join us on Calton Hill to see it with your own eyes, as it were. Join the live stream that Mark mentioned using the Cook telescope. And you can use Stellarium again to test and check times for your location. Now, I will give the official warning. Everyone should be well aware of this, but I'll repeat it anyway. Never look directly at the sun without appropriate equipment, and that applies to the Mark I eyeball and all of your optical devices. So it's just as well that Mark's got a bag of glasses to hand out. And if all else fails, then you can again use Stellarium to help you visualize what the eclipse might look like if you're not able to see it in person or join the stream. So let's have a look at that. So very similar to the previous script. I've set the time to the 29th, just before the eclipse starts. And now we're going to go and have a bit of a zoom in and see what happens. And now we'll sit for 2 hours whilst that plays through. Well, fortunately, what you can do with Stellarium is you can adjust the speed at which time passes. And so I've speeded this little movie up, and this is the eclipse happening. So, worst case scenario, if the weather's against us, then at least you can go back and watch this again and say, oh, that's what it would have looked like. And that'll just play through to the end, and that's the end of the eclipse. Okay, so that's the what we used to call, when I was a kid growing up, that's the big light. What about the night light? What's the moon up to this month? Well, first quarter was yesterday on the 6th, and the moon was visible for something like 20 hours on the trot. And I don't know why I found that hard to believe. So I went and played that through in Stellarium, not at normal speed, obviously. And it's true, when you turn Stellarium into a view that gives you an all-sky view, you can see the moon tracking around hour by hour until it eventually does set. So yeah, try that at home when you go home. The other important events from a lunar point of view, Full moon on the 14th. There's something else happening on the 14th as well, which we'll go on to in a second. Last quarter on the 22nd, and then the new moon on the 29th. So the other thing that's happening on the 14th is a total eclipse. This will only be partially visible in Edinburgh for reasons that we'll see in a second. And it'll also need either a late night or an early morning if you want to observe this. It kicks off just before 4. So again, let's use stellarium to see what this might look like, and we'll see what happens at a certain point in the process. So again, setting the clock to just before the eclipse starts, and then we're going to ask stellarium to jump to the moon. And there it is, complete with some nice labels, which we'll come back to later. And now I'm going to play that trick now. It's not a trick now, you know it. I'm going to wind the clock up, and we're going to play through and see what happens when the eclipse begins. And at this stage in the proceedings, I've still got the landscape turned on in stellarium, just that you can't see it because we're zoomed into the moon, but that's going to change partway through the eclipse. And there we go, we've gone underground. So that's the point at which the eclipse is no longer visible from Edinburgh. But using the magic of stellarium, I can turn the ground off. And that allows us to keep time playing through, and we can see the end of the eclipse as the moon starts to move out of Earth's shadow. And there we go. Save the difficult questions till the end. I think it's fair to say it's a simulation. Okay, what else about the moon? Well, I've always been fascinated by the moon. I think mainly because it was one of the things that I could find in the sky. But there's an awful lot to it. There's a lot to observe, and we've got a couple of things on our website. We have the ASE Lunar 100 and the first part of the ASE 24, two great resources to get you started on lunar observing. And as I've shown, using things like stellarium can help you. So check out the website stuff if you haven't done that for a while. Either side of the eclipse, there were a couple of other observable things that I pulled out to share with you this evening. And the first of these is an example of a clair-obscure effect. I think it was it Mike who posted a couple of messages recently about the X and V clair-obscure effects that we can see. Well, this is another one. This is the jeweled handle, and it's best observed around the 10th of the month, and this effect is caused by the light striking the Jura Mountains, and they're near to the Sea of Rains, quite close to L14 from a Lunar 100, and if you struggle with those directions, it's at the top left. As I say, best observed around the 10th of the month. So the effect will be that you'll see that curved mountain range. Oh, let me use another little gadget. Let's turn on the laser pointer. This little curved mountain range here will light up, giving that jeweled handle effect. The second example is called Valles Capella and the wider Capella crater complex. And they're located between the Sea of Tranquility and the Sea of Nectar, close to the lunar 108 and 25 items. Again, if you want to use my simple navigation, it's near the bottom right. And so this is down in this part of the lunar surface. And the Valles Capella is a rift that runs through the main Capella crater. So as you can see, there are labels on the moon in Stellarium. I've already said it's one of my favorite pieces of software. There are other lunar atlases are available, such as Moon Atlas, but it's a great way to explore the moon and start to find your way around, in addition to the resources on our website that I've talked about. Okay, let's move on to what I've called planetary shenanigans. So which of our planets are around this month and who are not? Well, first of all, after the planetary parade party made the mainstream news, both the evening and the breakfast bulletins, which is unheard of, February is clearly going to be a tough act to follow for planetary observing. There were numerous gatherings during February, as Mark pointed out, and that Andrew championed. So the question is, after that big planetary party, are we heading for a planetary hangover in March? And the answer is, well, yes and no. It's certainly quieter. A couple of our planetary friends are shy this month. Neptune's not observable, and neither is Saturn, which is a bit disappointing given that its rings will appear edge on, or would appear edge on from the 23rd of March. Not visible due to the solar conjunction. The rest of the planets are still reasonably well placed, Mars and Jupiter in particular, and there are also a few occasions where the planets are still getting together, albeit in smaller groups, possibly just discussing how much fun they had getting together in February. And there's one or two individual performances. The planets which are visible are best observed as early as possible in the month, although Venus will return towards the end of the month. Venus is in that image. It's just that the phase is at 5%, so it doesn't appear very well. And I did intend to take a closer look at that in Stellarium, but I don't think that'll show up very well, so I've decided at the last minute to skip that. So let's talk about some of those get-togethers then, some of those planetary conjunctions. The first of which is Mercury and Venus between the 9th and the 13th, early in the evening, just after sunset. So again, I'd revert to my trick of having a look at that in Stellarium to see what it could look like. Just double check. Okay, so for this little movie, we jump to the 9th at 7 p.m. and we have a look to see where Mercury's at. And there Mercury is, and the bright blob, can I say blob? The bright blob just above and to the right is Venus. It's quite low in the sky. And if we want to have a look and see how that changes between the 9th and the 13th, we can just take a flick through the days between at the same time for the rest of the next few days. And you'll see that Venus is dropping to near the horizon. So by about the 16th, it'll be pretty low. So that's the time to see that conjunction, just after sunset, around about 7 p.m. if you're in Edinburgh. If you're not in Edinburgh, then use these tools to find out the best time for your location. Much earlier the same day, at 2 in the morning on the 9th, Mars and the Moon will be in conjunction in the west. By 7 o'clock that evening, they will still be close together, but over in the southeast. And again, we can step through time using stellarium to see how this plays out. So similar kind of thing, setting the time to the time that's relevant for us and doing a search to find Mars. And I can just see, yeah, so that's showing them in the west. We can jump through time an hour at a time to see how things change. Obviously, one of the things that changes is it becomes daylight, but the two bodies remain close together throughout the day and then become visible again in the evening. And by this time, they're over in the southeast. Okay, moving away from the planets and thinking about the wider sky, what are the naked eye highlights and what's deserving of a deeper look? So this view shows the picture south on the 8th of March at 10 o'clock, and we can see Jupiter in Taurus over here, and we can also see the Moon and Mars together in Gemini. And our favorite winter constellations of Taurus and Orion will remain visible in the early evening, but by the end of the month, they'll be below the horizon after midnight. And we highlighted on the Sky Diary Leo as the next kind of prominent constellation. We don't really want to skip through Cancer. There's quite a few things to see in Cancer, but we've highlighted Leo, so I thought it would be useful to take a look at what's in Leo and see what we can find. So first of all, the recognizable backward question mark or sickle asterism is the head, mane, and the front paw of the lion, with the star Regulus at the paw, magnitude 1.35, marking its paw. The body and tail of the lion are just as recognizable. We'll come back to more details in the tail a little bit later. So Leo will be visible in the south all month, traversing from east to west every night. There's plenty to see. Again, we'll have a look at that in a bit more detail later. In the meantime, worth pointing out that the second brightest star in the constellation at Leo's neck there, Algebra, is actually a true binary star with magnitudes 2.3 and 3.6. Now, you need a reasonably sized telescope to resolve these two stars, something like 6-inch scope, or at least an optical setup that can deliver magnification of a couple of hundred. And I did try to see what that would look like in stellarium, and it was pretty messy. It was just two big white blobs. So yeah, sometimes you have to resort to the genuine optics. So raising our eyes from Leo and looking directly overhead, we come to Ursa Major, obviously circumpolar, which contains the plough or the saucepan asterism. Now, a question for the audience, does anyone actually call it the saucepan? Is that an American thing? Maybe. I thought I'd ask. We'll come back and take a more detailed look at the sky, that part of the sky in a second. Drawing a line from the final two stars in the plough takes us to Polaris, as we know, and then jumping to the other side of Polaris, we come to the recognizable constellation of Cassiopeia, the W shape. And I think that doing that kind of hopping in isolation a month at a time is a great way to build familiarity with different parts of the sky. As you've seen, I use Stellarium quite often to do just that kind of thing. And I can come back to some of the things that I've done with Stellarium in the member session next month if there's any interest in seeing that. Okay, let's go back to Leo and see what we can find when we take a closer look. So Leo and the nearby Leo Minor are home to a collection of many deep sky objects, including 5 of the 110 Messier objects. And the Leo triplet, just below the tail here, contains 2 of these objects, M65 and M66, along with the NGC 3628, the Hamburger galaxy. M65 and M66 can be seen through a pair of 10 by 50 binoculars, and mid-month is the best time to view them. This shows the view south on the 18th, and as luck would have it, I managed to get an image of the triplet using my Dwarf 3 telescope earlier this month. So this image contains a couple of hundred of 15-second exposures. We've got M65 and M66 and the Hamburger galaxy up here. And this was stacked by the Dwarf and processed lightly in Lightroom Mobile. Now, there's an excellent image of the Hamburger galaxy, which was captured by our Azero facility and processed by John Briggs, and it's on the main ASD website. So again, I'd have a look at that. It's an amazing image. Also, within or near the body of Leo are M95 and M96, which make a great pair of imaging targets. So yeah, explore Leo during March and see what you can find and come up with. Okay, let's go back to Ursa Major. If we look to the east, staying at 2200 hours on the 18th, we can locate the Owl Nebula. And this is a planetary nebula. It's there, magnitude 9.9, about 2,000 light years away. And again, I've imaged that with the Dwarf telescope on the same night as I took the Leo triplet. But as you can see, it's a pretty small target for this size of scope. It is there, I promise you. Again, about 200 exposures, 15 seconds, and a little bit of processing in Lightroom. Now, what I did find as I was doing this was that I found that I'd also captured M108, the Surfboard galaxy. And it's one of the fainter Messier objects, about 46 million light years away. So it was a nice bonus to capture that in the same image. That doesn't often happen. So you'll take those good wins when you can. Also wanted to highlight another image of another Messier object in Ursa Major, M81 Bode's galaxy. Now this is a spiral galaxy, magnitude 6.9, about 11.8 million light years distant. And this image is striking for a couple of reasons. First of all, it was captured using C-Star S50 telescopes, so small, smart telescopes. And secondly, it was collected using multiple scopes. So Mike Christie and Tim Honeysett captured the data, and Mike did the processing. And this contains 10 hours worth of data. And so the reason I think this is striking is that it demonstrates both the capability of these small devices and the power of collaboration, what we can do when we bring stuff together. And there's a couple of other images that have been done, and there's work underway on more. So anyone who's got a smart telescope, get involved and let's kind of pool the data and see what Mike can make of it with his PIX Insight magic. Okay, let's come back to the clock events then. Two time-related things happening in March. First one of those is the equinox. Now, meteorologists consider the 1st of March to be the first day of spring. And if I remember rightly, the first day of March was a pretty nice day, so it was a good candidate to be the first day of spring. However, we astronomers use the vernal equinox to mark this milestone. And this is the moment when the sun crosses the celestial equator, the imaginary line in the sky from Earth's equator, from south to north. During the equinox, the Earth's axis is perpendicular to the sun's rays, meaning that all regions on Earth receive about the same amount of hours of sunlight, well, at least in principle. It's called equinox because it's derived from the Latin, meaning equal night, but the literal translation isn't correct. In reality, the equinox days don't have equal hours of daylight and darkness. That happens on an event called the equilux, but no one seems to talk about that. So for now, we'll just stick with approximately. It's also important for other reasons that we'll get to in a second. The other clock-based event is the beginning of British summertime, which, when I was writing this down, thought, well, spring starts on the 20th, but summertime starts on the 30th. That doesn't leave us with a very long spring. I don't know why that came into my head, but there you go. So 1 a.m. GMT on the 30th, you either lose an hour in bed or you lose an hour's worth of observing time, depending on your predilection. It's a bit of a no-win situation, but the good news is we'll get the hour back in October. So March might be another occasion when we are treated to some spectacular views of the aurora borealis, but I'll stress the might just in case. And what are the reasons for this? Why might that be the case? Well, first of all, the sun is close to the solar maximum, the peak of its 11-year solar cycle. And the second reason, as we've just learned, the Earth's axis is perpendicular to the sun's rays. So there's an opportunity for more solar energy to enter the atmosphere. So keep your eyes on the northern sky at night, obviously, around March the 20th, days and weeks either side of that. And if you'd like to be alerted to any aurora-based activity, then you can use the Aurora Watch app and get the alerts, or you could join our WhatsApp group and get all kinds of alerts about all kinds of stuff. These images were captured using my iPhone back in May of 24, just handheld 3-second exposures. So it's pretty easy to get some striking images. So let's hope for some activity from the aurora this month. So that brings me to the end of this Sky in March session. So let's finish with a summary page. Here are your March highlights. All-nighter or early start for the lunar eclipse. Full moon on the 14th, but things to look at either side. Solar eclipse on the 29th. Come and join us in person or watch the live stream. Clock's going forward, summer is coming. Planets, a little bit subdued after their big bash in February, but still plenty to see. And from a sky point of view, look out for Leo and the owl, and stay alert around the end of the month. If you found any of my pointers using Stellarium helpful or irritating, then let me know, and perhaps I can do a show and tell about that at the members session next month. And with that, thanks for listening. Have a great month, clear skies, and see you soon.
Thank you, Neil. I think Stellarium worked really well, actually. I enjoyed that. And that's it for Hugh.
Very quick, 30-second advert.
Okay.
No slides, no nothing. Thank you. Hi there. 1st of April, Tuesday, 2 o'clock in the afternoon, Linlithgow at the Cathedral, I think it's the Cathedral Church. Dr. Catherine Sullivan is going to do a presentation. She flew on STS 41, 31, and 45, the space shuttles, so pre the ISS. Fantastic speaker. I've seen Tim Peake and I've seen Chris Hatfield and can't remember the other one. Anyway, there's tickets available, or there were. Help yourselves, I'm going.
Thank you. Okay, thank you, Neil. Thank you, Ben, again. That was really, really good talk, and obviously lots of interest with that as well. There's tea and coffee at the back as well. We need to be out of here by 10 o'clock, but lots of time, so see you at the next meeting.